Today we're going to take a look at a very fundamental circuit that you'll find used a lot in analog design, which is the precision rectifier. Now, if you've ever played around with a crystal radio set or a power supply, you're probably already familiar with rectification circuits with passive diodes, where they take in some AC signal that's swinging above and below 0 volts, and they rectify it so that the output is always above 0 volts. Now, the precision rectifier does the exact same thing, and it uses diodes to do it. But the advantage of adding the op amps here is that the op amps can account for the voltage drop across the diode, so you're not losing 0.6 volts or 0.7 volts. And you can also get some gain out of the circuit as well. So let's go over to the whiteboard and take a look at how this works. So let's start by taking a look at a simple and somewhat naive half-wave rectifier using an op amp and a diode. Now if we have some AC signal coming in, we have an inverting op amp configuration here. So when the AC signal goes high, the op amp's output is going to invert that, so it's going to be low, it's going to be negative. And that's going to reverse bias this diode, so we'd expect to see nothing on the output. And then when the signal goes below 0 volts, when it goes negative, of course the inverting amplifier will flip that, so it'll be positive. That will forward bias this diode, and the output will be positive. And of course that pattern will just continue repeating, so we have this nice half-wave rectified output. Now this is what we would expect from any half-wave rectifier. The advantage that we get by adding the op amp in is that the forward voltage drop across this diode is automatically accounted for. So the forward voltage drop, first of all, is not very predictable. It's going to change from one diode to the next. It's also going to change based on the amount of current going through the diode. So if you want a precision rectification where the rectified output is really closely matched to the input, just using a simple diode is probably not going to work. However, with the op amp here, it's going to drive its output to overcome any losses in the diode because we're taking the feedback from right here. We're not taking it directly from the output of the op amp, we're taking it from the other end of the diode. So we have, if we assume R2 and R1 are equal value resistors, a unity gain amplifier. So the op amp is going to drive this point until it is equal to the input. And so it's going to drive its output then slightly higher in order to overcome the voltage drop of the diode. And of course, if we make R2 a little bit larger, we can get a bit of gain out of this circuit as well. But as I mentioned, this circuit analysis is a bit naive, so this circuit is not going to work exactly as you might expect. So let's go over to the bench and take a look at what really happens. Now with a 100 Hertz sine wave being fed into this circuit, we would expect that the negative going portion of this input would be positively rectified because we have an inverting rectifier. However, if I turn on channel 1 here to see the output of the circuit, we actually get full wave rectification. So the negative going portions of the input signal are rectified just like we expect, but we also have the positive going half of the input sine wave as well. Now you might think, oh hey, this is great, I get free full wave rectification, and that's kind of true, but there's a couple of problems with this. First of all, notice that the only load I have on the output of the op amp is the high impedance input of the scope. Now if I put a much lower load on the output, such as a 220 ohm resistor, you'll see that all of a sudden we get that half wave rectification that we were expecting. So those positive going excursions are suddenly attenuated when we put a lower impedance load on the output of the op amp. Another thing to bear in mind, and I'll turn off channel 2 here so we can kind of see it a little more clearly, is that this output, and this is the expected output, this is the inverted rectified half of the input that we expected to have on the output of the circuit, doesn't quite track the input at the very beginning. So you can see instead of having a nice kind of half of a sine wave here, we get this sharp uptick and then we start tracking the input sine wave. And this is true even if we have a high impedance load on the op amp, so we get kind of that full wave rectification. You can see that right here we shoot down below 0 volts and then suddenly we shoot up above 0 volts before we start tracking that half of the input sine wave. So we're getting some error here. Now, what's going on here is when this diode becomes reverse biased, it's effectively removed from the circuit. So the op-amp has lost control of the feedback loop here. Now, we had assumed in our previous analysis that this would result in 0 volts output, but it doesn't because we have a path from the input signal to our output here. And since this is effectively removed, we have the signal traversing through R1, through R2, and to our output. So that's why we're getting this full wave rectification. When that diode is forward biased, sure, the op-amp takes control and we get the expected half wave rectification, but when the diode's reverse biased and removed from the circuit, the op-amp no longer comes into play, and we've just connected our input signal through these two resistors to our output. So that's why we're seeing the positive half of the input signal on our output. It also explains why when we put a stiff resistor here as a load, that positive half of the signal effectively disappears because we formed a voltage divider between these two series R1 and R2 resistors and our load. Now, in my circuit, I was using 4.7 kilo ohm resistors for R1 and R2. So putting a 220 ohm resistor as a load effectively created a voltage divider that really just knocked the signal down to effectively 0 volts. And we can see this very clearly on the scope if we connect channel 2 in green here to the output pin of the op-amp. You can see that when the input has that positive voltage excursion, the inverting op-amp is driving its output pin all the way down to its negative rails, just driving it straight down. And when that signal starts going negative again, the op-amp is trying to drive its output back up. But it's not quite fast enough in this case to drive its output up quickly enough for us to not notice. And you can see that this rising edge of the op-amp's output corresponds very nicely to this glitch that we're seeing here. So that's exactly what's happening on the output of the op-amp. And if you have a very high slew rate op-amp, you might not notice this. Now in this case, my input signal is only 100 hertz, but my op-amp is an LM741, which I specifically selected for this example because it has a very low slew rate, and even at low frequencies, this little glitch and error in tracking the input is very obvious. Now, to prevent this, we could try and pick an op-amp with a much faster slew rate, but a better solution is to add a second diode here. So the problem is, of course, when the op-amp's output goes negative, it's driving all the way into its negative voltage rail because this diode's reverse biased and the op-amp has lost control of the feedback loop. Adding a second diode here means that when the op-amp's output starts to drive negative, it only has to drive negative far enough to forward bias this diode, at which point the input and output are shorted and it has a feedback path, and it's just going to hold this at 0 volts, which means this point, since there's a 0.6 volt drop across the diode here, only has to drive down to about negative 0.6 volts in order to do that. So with the addition of that second diode, we can see that this waveform is exactly what we had originally expected to see on the output of the circuit. And we can see that that glitch is now gone. So if we turn on channel 2 here to look at the actual output pin of the op-amp, we can see that, yes, the op-amp still has to drive positive very quickly, but it doesn't have to go all the way from its negative rail up to 0 volts. It only has to go from, this is about 0.5 volts, up to 0 volts. So it has far less distance to traverse, and so it can catch up to the input much more quickly. So in this case, the error here is almost imperceptible, even with a low slew rate op-amp like the LM741. So that is your basic half-wave precision rectifier circuit. Now, of course, the precision is going to depend on the input offset errors of the op-amp, as well as the matching between these two resistors, but it's going to be typically a lot better than just using diodes to get your half-wave rectification. You can also configure this to have a bit of gain or attenuation just by changing the ratio of these two resistors, as with any inverting op-amp configuration. However, sometimes you really need full wave rectification instead of half wave rectification. And it's actually pretty easy to go from this circuit to a proper full wave rectifier. All we need to do is add a summing amplifier. So this portion of the circuit in blue is what we've already seen. This is our half wave precision rectifier, and the diodes are configured here so we get a negative output. Now that output is fed into the summing amplifier through this resistor, which is 1/2 the value of this resistor. So because it's 1/2, we're going to have a ×2 gain here. The original input waveform is also fed into the summing amplifier, but it's configured with a gain of 1. So this resistor that the input signal is fed into is equal to this resistor here. So this ratio of a 2-to-1 gain between these two inputs to the summing amplifier is what makes the full wave rectifier work. So let's say that our input signal is 2 volts peak to peak. We get +1 volt and -1 volt. Well, when this goes positive on this positive half of the cycle, this rectifier is going to invert that, and we're going to have a -1 volt peak here. At the same time, that +1 volt peak is going to be fed in through this path to the summing amplifier. So we have a +1 peak voltage here that goes through a ×1 summing gain. We have a -1 peak voltage that goes through a ×2 summing voltage gain. So we have 1 volt plus -2 volts, which gives us -1 volt. But of course, this is an inverting amplifier, so our output is going to be +1 volt peak. On the other hand, when the input signal goes negative, we're going to have a -1 volt peak here. Of course, this just outputs 0 volts on that waveform because the negative input is inverted, and that reverse biases this diode. So we're going to get our 0 volts out here. So we're going to have 0 times 2, which is just 0, plus our -1 volt here, which is ×1. So we're going to have -1 plus 0, which gives us -1 on the summing input. And then the inverting amplifier inverts that to be a +1 excursion. And this cycle just keeps continuing. So we get a full rectified waveform output just by adding a summing amplifier and ensuring that the original signal input here and the rectified or half-wave rectified input here has a 2-to-1 ratio. So as long as that ratio is the same, this works. It doesn't have to be a gain of 2 or a gain of 1. So we can make this, say, 10 times larger. So this could be 10R. And so then we would have a gain of 20 and a gain of 10, which would ultimately give us a gain of 10 on the output, but we'd still get that nice rectified output. And if we build this up on the bench, we see we get exactly that. We have a 2 volt peak-to-peak input signal here, and we have a full wave rectified output of 1 volt peak. And this is useful not only for absolute value conversions or detecting the amplitude of an input signal, but also for frequency doubling. So if you look, by performing a full wave rectification, we've effectively doubled the frequency. And this works particularly well with triangle waves since they maintain the nice 50% duty cycle. So this is your classic precision full wave rectifier circuit. And there are different circuits that are very similar that are configured for high input impedance. There are also some that only use one op amp or only require 2 matched resistors instead of several matched resistors. But they're really all variations on a theme. So if you understand the fundamental basic circuit, the other ones will follow. So if you have any questions, suggestions, or corrections, as always, leave them in the comments section below. And thanks for watching.